Hi, this is the midterm review, and as always, I am the amazing Mr. Jansen, so away we go. If we look at this first one, we're asked to write the equation of a line that's parallel to y equals 3x minus 1 and passes through 1, negative 2. So the two things that I need to write the equation of a line are the slope and the y-intercept. For this one, the slope, since these two lines are parallel, the slope is going to be the same, so it's the positive 3. And then for the y-intercept, I do a fresh y equals mx plus b, and I just plug in what I know. I know that the slope is a 3. I know that the x and the y value are right here. It's this ordered pair that we're given. So I plug a 1 in here, negative 2 in here, and I just have to solve this for b. So I subtract the 3 from each side, and I find out that b equals a negative 5, which means my equation is y equals 3x minus 5. And that's it. Number 2 is very similar. I still need to find the slope and the y-intercept. The only difference is this time I'm given a line that's perpendicular. So this line has a slope of 1/2 perpendicular. I do the opposite reciprocal. So I change it from a positive to a negative. And I change it from a 1/2 to a 2/1. So I make it a negative 2. So I change the sign and flip it. And then I still do the same thing. I fresh y equals mx plus b. Plugging in what I know. I know the slope. I know the x and the y value, because once again I'm given an ordered pair here. So I plug in the negative 4 and the positive 3. That's going to give me a 3 equals a positive 8. That's terrible looking. Let me try again. A positive 8 plus b. I subtract the 3 from each side. Or sorry, I subtract the 8 from each side. So I find out that b equals a negative 5. I get y equals a negative 2x minus 5. And that's it. Number 3, it asks me to write the equation of a line that passes through 2 points. Once again, this is the same thing, except the thing that changes is how I find the slope each time. All right, parallel, the slopes are the same. Perpendicular, slope is opposite reciprocal. Given 2 points, I use my slope formula. I do the change in y over change in x. So I look at my y values. I over change in x. My y value was a negative 2. Now it's a positive 10. It's gone up 12. So I put a positive 12 down. My x value was a 1. Now it's a 4. It's gone up 3. So my slope is 4. And then I use a fresh y equals mx plus b. Plug in what I know. And it doesn't matter which of these ordered pairs I use. I can use either one. I'm going to use this one just because they're smaller values. Plug the 1 in here, the negative 2 in here. So it looks like I get a negative 6. So now my equation is y equals the 4x minus 6. And that's it. For this one, it's asking, is this a function? And so when we look at this relation, which is just a set of ordered pairs, to determine if it's a function, I need to check to see that every input has exactly one output. So essentially, I'm looking for x values to make sure they only have one y value. And if I look right here, these are the ordered pairs that give it away. The negative 1 has a y value of 1, but then the negative 1 also has a y value of 5. So this one is not a function. For it to be a function, I need faithful x values. I need x values that are only with one y. So this one's not a function because the x value, because the negative 1 is with 2 different y values. Okay. The next one is asking us, is the relation a function? And when we have a graph, we're just going to do our vertical line test. So if I were to take a vertical line here and try passing it over to the function, I drag this across the function to see if it touches 1 point at a time. And in this scenario, it does touch 1 point at a time, which means this one passes the vertical line test. So yes, this one is a function because it passes the vertical line test. And really what the vertical line test is doing is it's testing to see if each x value has exactly one y value. If it touches more than 1 point at a time, that means that x value has 2 different y values. Okay? And number 6, we just want to simplify this thing, so we're plugging in the values. So I plug a 6 in for y, a 5 in for x. a 7 in for z, and a 40 in for w. And now I just need to simplify this thing. Order of operations, I start inside the parentheses. That's an 11. Here, that's a 121. Over here, when I multiply this guy out, it looks like it gives me 1,400. Then I add them up. That gives me a 1521. And that's it. The next one's asking me to solve. Whenever we have an absolute value equation, we have to split this into two. So I'm going to split this up. The first one is 3x plus 6 equals 12. The second one is a 3x plus 6 equals a negative 12. Because remember, what's inside the absolute value could be the positive or the negative version of that 12. So that's what I'm saying. What's inside here, the 3x plus 6, could be the positive version or the negative version. And then I just solve each. I subtract the 6 from each side. I divide by the 3. Over here, I subtract the 6 from each side and divide by the 3. So I get two answers, a negative 6 and a positive 2. Okay? Number 8, I want to solve the system of equations, and I can either use substitution or elimination. Substitution would work great if I had an x value or a y value that was almost by itself. This one, elimination, works great because if we look at these y values, I've got a negative 3 and a positive 3. So I'm just going to add these two together. And what happens when I add these up, I get a 5x. The y values cancel each other out. Elimination equals a 10. I divide each side by the 5. So I find out that x equals 2. And that's great, but I'm not done yet. I have to plug that 2 back in. And I can use either one of these equations. I'll use the second one, so I plug the 2 back in for x. And now I can finish solving for y. So I get 4 plus 3y equals 1. Let me bring it off to the side here. I subtract the 4 from each side. And then I'm going to divide by the 3. So I find out that y equals a negative 1. Okay? And a nice, neat way to write these answers is as an ordered pair. So I'd write this as the ordered pair 2 comma negative 1. Because if we're thinking about this in terms of a graph, we're thinking about where these two lines cross one another. And number 9, we're just doing some simple multiplication. So I'm going to multiply these first two. I multiply the numbers. 10 times 6 is a 60. When I multiply, I add the exponents. And keep in mind, this is an x to the first over here. So that's going to be an x to the third, y to the third. And now I'm just going to keep multiplying. I'm going to multiply it by the second piece of this thing. I follow the same rules. I do the 60 times the negative 7. That's going to be a negative 420. I add the exponents. That's x to the negative 12th, y to the 8th. Sorry, y to the 11th. And now the last thing I have to do here is take care of negative exponents. Remember, a negative exponent is simply a way of writing division. This would be over x to the 12th. Okay, I send that exponent, I send that whole term to the denominator and make it positive. Okay? And number 10, I can't add or subtract radicals unless they're like radical terms, which means they have to have the same radical symbol with the same number underneath. And these don't, so what I'm going to do is I'm going to simplify these as far as I can. The 12 is the same thing as 4 times 3, and 4 is a perfect square. For the 27, perfect squares that divide evenly into 27 is a 9, so 9 times 3. And then for the 50, perfect squares divided evenly into 50 are 25, so 25 times 2. And now I start taking the square root. The square root of 4 is a 2, goes to the outside, it's a changed number on the outside. The 3 is still trapped. The square root of 9 is a 3, goes to the outside, it's a changed number on the outside, but this other 3 is still trapped. The square root of 25 is a 5, jumps to the outside, the 2 is still trapped. And now I have like radical terms with these first two. And when I add like radical terms, I add the numbers that are out front. The radical part stays the same, so that's going to be a 5 root 3. This one, the 5 root 2, I can't do anything with that because that's not a like radical term. So that one's going to stay exactly the way it is. Okay? For the next one, I'm looking for perfect squares that divide evenly in here, and I want to find the largest perfect squares that I can. The 32 I can break down into a 16 times 2. For a variable to be a perfect square, I need exponents that are divisible by 2, so I'm going to break this down to an x squared times x. Y to the 8th is already a perfect square because it's got an exponent that's divisible by 2. Now I start taking the square root. The square root of 16 is a 4. The square root of x squared is x. We're assuming all variables are positive. The square root of y to the 8th is y to the 4th. Again, we're just dividing each of the exponents, and that just goes back to our rules of exponents. And then trapped underneath here is the 2 and the x. And that's it. For number 12, the square root of a negative 81. Well, the square root of 81 is a 9. That's easy. So the square root of a negative, remember, that's an I. That's an imaginary number. So that's 9i. And if you want to think of it this way, if you want to break it up into the square root of 81 times a negative 1, that's fine. The square root of 81 is a 9. The square root of a negative 1 is an I. And notice there's still nothing left under that square root, so it's a 9i. That's how we get imaginary numbers. For this one, I want to use my distributive property, so I'm distributing this term. And keep in mind, when I have a radical term, the 3, the thing that's out front, is just like a coefficient. And then the radical part kind of associates with the radical part. Just like I deal with these things, if I had a 3x out here, I deal with the number and the variable separately. I do the same thing here. And remember, it's just stuff on the outside with stuff on the outside, stuff on the inside with stuff on the inside. So when I do the 3 root 5 times the 2 root 6, I do the 3 times 2 on the outside, which is a 6. I do the 5 times 6 on the inside, which is a 30. And I do the same thing with the next term. The 3 times a negative 3 is a negative 9. The 5 times the 2 gives me a 10 underneath. And now I would simplify this as far as I could like I did in number 10. I'm looking for perfect squares, trying to combine like radical terms. And there are no perfect squares. There are no like radical terms. That one stays exactly the way it is. Okay? This one I want to distribute or FOIL here. So I'm going to distribute the 2. When I distribute the 2, that gives me an 8 plus 4i. And now I distribute the negative 3i. That gives me a negative 12i minus 6i squared. And now I can combine like terms here. That gives me an 8 minus 8i. But then right here, the negative 6 times I squared, keep in mind that I squared is actually a negative 1, which means what I have here is negative 8 minus 8i plus 6. And now I have more like terms I can combine, which means what I truly have here is a 14 minus 8i. And that's it. For this one, it asks us to factor completely. So the first thing I always look for is the greatest common factor. For this one, it's a 3. So I factor the 3 out, which leaves me with an x squared minus 4. And then when I look at the x squared minus 4, that is a difference of squares. So I'm going to factor that into conjugates, an x plus 2 and an x minus 2. And now nothing else can be factored. So now this one is done. For number 16, x cubed minus 27 is one of our special cases. That's a difference of cubes. Remember, this is one of our SOAP problems. So I factor this into a binomial and a trinomial. I fill in the signs, and that's where SOAP comes in. Same, opposite, always a plus. Okay? So this sign is the same, minus sign, the opposite, and this one's always a plus. So I fill in my signs. And now for the binomial, the thing up front, I take the cube root of each of these. The cube root of this first term is going to give me an x. The cube root of the second term is going to give me a 3. And now I kind of have to make it work. If I take the x and square it, it's an x squared. If I take the 3 and square it, it's a 9. That's the first and the last term. And then the middle term, I take the two values from the binomial, the x and the 3, and I multiply them, giving me a 3x. Okay? That's how we factor a difference or a sum of cubes, using SOAP, memorizing this pattern, and then filling it in. Okay?